Hi, this video is going to cover 13.2, which is perpendicular and angle bisectors. All right, so we have a couple different theorems that talk about perpendicular and angle bisectors, and we have constructed both of these, and I'm going to go over real quick kind of what they look like and what these theorems tell us. So we've used our compass and our protractor to construct them before, and I am going to show you with this is theorem 25. And I hate calling them by their theorem 25 or whatever because each book is a little different, but theorem 25 for bisector theorem is what this one's called. So if we had a line and we want the perpendicular bisector using our tools, so we just have a line, I'm going to take my compass and I got to make sure that it is set at least greater than halfway, and I'm going to put it at the end, which at each end, and I'm going to make a little arc. So I got to move my paper for this one because it works better that way. All right, there we go. So this is the kind of the arcs that you make, and we'll just call this point A and point B. And where these two cross, here and here, you can form a line, and it happens to be the perpendicular bisector. So it hits this line, and it's perpendicular, and it's a bisector. And so that means this side and this side are congruent. So we know how to construct this in case you're asked to construct something, which I think you are maybe in your notebook, but either way, remind you how to construct it. So let's say we have this, and let's call this point right here. Let's just call that point P. Let's say we have something, you wouldn't have the arcs, that was just how I drew it, but what if your rule or your theorem said you have line PM, we'll call this M for, and we'll just call this a line, but and it is perpendicular to AB, and you also have that MA is equal to MB. So basically MA and MB, you have the perpendicular bisector. If you have this, so this is a big if, then the following is true. So how long did I make that one? Just so it looks about the same as I draw it. I'm going to construct it pretty just because I like things to be exact. You wouldn't have to do this just to draw it, but you know, some of us like exact when we draw things, especially for the class. All right, it says if I take and form a triangle from that point P. Okay, so see how those look the same, except I added in the triangle. I just connected those. So this would still be A, M, B, point P. And we know these are perpendicular bisector there. If we had that information from the beginning, then if we drew these triangles, then these sides would be congruent too. So PA is going to have to equal PB. So if you have this, then you could draw that triangle, and these two sides have to be equal too, and you have a nice isosceles triangle. All right? So that's theorem 25. Theorem 26 goes the other way. If you have if you have this congruent to this, so if you start out with, I'll still call that P, A, B, and this is theorem 26 for our curriculum. I think I need to put this over, just there we go. So if you have this, so you have PA is equal to PB, then you're going to also then have a perpendicular bisector from P to AB. So then we know So it's like the opposite way. So it's kind of like a, this theorem basically goes both directions. Oops, I didn't do very good drawing this one. Oh, well, it's not quite the same. It's meant to be the same, but I was hurrying and did not make it look exactly the same. All right. So if you start out with these two sides and you draw a perpendicular down, it is going to bisect and be the perpendicular bisector from that point P. So then you would have PM as perpendicular to AB. You would also have MA is equal to MB. Right? So it kind of goes both ways. So where would I use this in examples for actual problems? I might have something like this. Here's a triangle, and we'll call this ABC. And the perpendicular bisector. Perpendicular, we know that's congruent to that. So we're given this, and you know this side is 4x, and you know this side is 2x minus 10. What is the length of AB? So how would I find the length of AB? Well, we know if these are congruent, what do we know about these two sides up here? They have to be congruent. All right, so those have to equal each other. We can find that x value. Then we could find what the length is of AB and BC. So we're going to say, all right, we know 4x has to equal 6x minus 10. All right, so I'm going to subtract the 6x this way so that all the x's are together. 4 minus 6 is negative 2x equals negative 10. Divide by negative 2 to get the x by itself, and it equals positive 5. So we found x, but that's not what it's looking for. So we have to then go over, okay, so for AB, I would have 4 times x, which is 5, so it's 20. So AB is equal to 20. What would BC be? Better be 20. 5 times 6 is 30, minus 10 is 20. They have to be the same because that's what the theorems tell us. So that's how you would use that one. The next one's an angle bisector, and this is theorem 27. And this one is similar. Theorem 27 and theorem 28 are like the same thing, switching just like those ones were. So this one is an angle bisector. So we got to start with an angle. Okay, so, and then it's going to have a bisector, and I'm going to construct this. Why am I constructing angle bisectors? So that you remember, as I do it, how to do it. Because we've already learned it before, but we have an angle, we want to bisect it. What we did was we drew an arc where our tip is at our vertex. Just doesn't matter what it's set at, there's an arc. And from each end where those cross, so you have a point where it crosses the exact same spot, you make an arc above. It doesn't have to be real big for both. And then where this point and the vertex meet is the angle bisector of that. Okay, so that means this one's congruent to this one. So we just constructed a really pretty angle bisector. And this, we also have some other information. I'm just going to use this point right here. I'm going to call that point S, and we're going to call this one Q. P, oops, no, I don't want P to be there. I don't really care about the end. Okay, then from S, I'm going to, I don't really feel like constructing all of these because it'll take me way too long. We are going to have, which is what a lot of you did on your homework last time, was you didn't actually do the constructions, you guessed, which means you didn't get them correct. So if I just guessed what the perpendicular was and I didn't actually make the arcs, then that's not really construction. But for this theorem, it says, all right, here's this point P, this point R. It says if QS bisects PQR, and we also have SP is perpendicular to QR, or QP, excuse me, QP. And our last bit of information we're given is SR is perpendicular to QR. So if we have two perpendiculars and this is the angle bisector, then we'll know that these two are congruent. So the picture, to make it the same, I'm going to kind of do my best to make it look the same. They're not going to be exact, but they'll be close. Whoop. Hey, not bad for freehanding it. Okay, so this is S, and this one's perpendicular. This one's perpendicular. And we have our labels Q, P, S, R. Then we know that these two are congruent. So the theorem tells us, all right, if these happen to be congruent, then guess what? These are congruent if they're perpendicular to the sides. Right? Okay, then SP equals SR. And the next theorem tells us, well, guess what? If you have these two, then you can imply that these two are also congruent and that these are meeting at a 90-degree angle. They're perpendicular, not a perpendicular bisector, just perpendicular. Okay, so it kind of goes both ways. So theorem 28 I'm not going to write out because it's just going both directions, but let's go ahead and look at some example problems where we'd use that. First of all, we had to remember how to draw it and do the perpendicular bisector. The next thing we're going to do is answer some questions with it. Oops. Okay. There we go. We have an R right here. And we have an M. And we have a P. It's going to be here. And we know this is a 90-degree angle. And this is 7x. And we know these are congruent. Okay, and this one is 2x plus 25. What is RM? So it's just going to give you different pieces and it's going to say, okay, where are they? So we know we're given that these two angles are congruent. So then we know that implies that these two are congruent because they meet at the 90-degree angle. And they have to tell us that. They have to tell us angles and 90s, or they have to start with these two already congruent. One or the other, right, to go either directions on using the theorem. So we know that these two have to equal each other, so we can find x and then find our RM, because we know 7x has to equal 2x plus 25. So we'll solve that. We'll subtract our 2x over, subtract 2x, and you get 5x equals 25. Divide, and you get 5. Hey, we got 5 on the last one. And then we take our 5 and we put it back in to find our RM. And we would have 7 times 5, which is 35. So we know RM is equal to 35. So looking at that, we could also be looking for an angle degrees. So this is my last example. You know, and these look scarier than they are. I mean, really, they're not too bad at all. You just have to remember that the theorems. So let's make this look like a 90. Okay. Somewhat looks congruent? That's okay. So if we're told that we have, can't even see it. Hello. If we're, see how this is a little off. Oh well. If we're told these are congruent and this one's 27, could you easily find this one? Well, sure. So we'll say that this is L, F, H, K. So we can label things here. You could easily say LF is 27 because it says they're congruent, so that's easy to find. Well, what if it asks for this one, and we know this is 6y, and we know this one is 4y plus 18, so we're given like another formula, right, basically. I would know these have to be congruent because these are congruent and they meet at the 90, so then we can imply that we'll know 6y has to equal 4y plus 18. So we'll minus the 4y over, and I'm going to get 2y equals 18. Divide by 2, and y is equal to 9. Now let's say we wanted these actual degrees of these angles. Well, 6 times y is going to give you 54 degrees for this one. And what does this one have to be? 54 degrees. Well, 9 times 4 is 36. 36 plus 18 is 54 degrees. So we're good. They're both 54 degrees. So that's kind of how you're going to use these angle and perpendicular bisectors and how you use them with the triangles.